So today I'll give you an overview of cell, which is a synchronous language inspired by STL. And I will start with an example now. I want to blink an LED like this on and off every 500 milliseconds. And what I can do in cell is to write an infinite loop that awaits this period and then makes a system call to toggle the state of the LED. So this is the behavior that I want in the specification. Then I want to stop blinking after a button press. So if I press the button here, the blinking will stop. And what I can do now is to use a parallel composition. Now we have two lines of execution. We call them trails in cell. And we are using the OR variation here. So when either of the two sides terminate, in this case, the button press, the other behavior, the blinking, is aborted, and we proceed to the next line after the composition. And now, suppose we want to restart everything after 2 seconds. So I have the blinking behavior, I press the button, and after 2 seconds, it restarts. I can press again, it stops, and after 2 seconds, it restarts again. So to implement this behavior, after the composition rejoins, we await other 2 seconds and enclose everything with another loop. So very typical, similar to STL. We use a lot this idea of compositions with sequences, loops, and parallels at any level of depth. So here we have a loop inside another loop. In between, we have a parallel composition with a sequence, and so on. And the idea is to avoid the use of state variables and explicit state machines in the code, and also avoid explicit communication between lines of execution. So as I said, cell is heavily inspired by STL. You can see from the previous code. So today I will focus on the peculiarities of the language. I will enumerate here 6 peculiarities, and I will go through them in the next slides. So external events, they define the notion of time, logical time in cell, as a queue of unique events. And this is important for our simple static analysis that if events are unique, we have mutual exclusion in the code. Internal events are very different from external events. The semantics is completely different. They create new interreactions inside the external reactions. They are based on a stack and not on a queue, and they allow us to build rich control mechanisms in the programs. Concurrency, we have internal determinism. It's very simple, simple stack checks as well. And we allow concurrent assignments and system calls based on this. I will show that later. Safe integration with C. The most important is how we enforce finalization for local and external resources. For example, when we open a file, external file, or when we send some buffer in the network, stuff like that. First class timers, we provide a dedicated syntax and automatic readjustment. So yesterday I saw a talk from Stephen Edwards, so the ideas are similar. Actually, a lot of things here are similar to his ideas, and not everything here is novel. So, and the last one is dynamic execution. I will not focus on this today because it's more complex, but there is a video in the website of Cell. So the first 5 items, they are described in this paper. So you have the curiosity, you can follow with this paper. So about external events, I will compare here the semantics between STL and cell. At least the classical STL, there are many variations that are similar to cell, but I will focus on the classical one to be easier to compare. So both have a discrete timeline, and we will show how they interact with the reaction in the actual reaction in the CPU. So typically the timeline in STHL uses fixed ticks like this, and we'll show how some external input events fit in the timeline as well as in the CPU reactions. First thing that is that both languages, they have this concept of boot reactions that execute as soon as the program starts. And as the inputs come, they are postponed to be handled in the next reaction. And then we have here both reactions in cell and STHL. And the first difference here is that we see that in cell, the timeline and the CPU reactions are always coincident. But in STHL, this is not always the case because the reaction can take longer or shorter than the ticks. So another difference is when we have here on tick1 in STHL, we had two external inputs, so they will be simultaneous in the next tick. And in cell, we will only handle one at a time. So here we see the reaction to B and C simultaneously, and in cell, only the reaction to B that also determines the logical time here. And so in cell, we still have to handle C in a new reaction, and this creates another logical unit of time. And time goes on, and during tick 2, we had no inputs, so we will have an idle tick in STHL, and in cell also a small period of idleness, but as soon as D arrives, we can interrupt and continue from there. So also a little bit different how these reactions go. So the semantics of cell is very typical in event-driven systems with callbacks and games and multimedia applications. It's not something very new, but it's important to distinguish from STHL. So internal events, as I said, they are based on a stack execution. So when I do an emit in the program, the next statement in the next line goes into a stack and does not execute. It actually makes a new inter-reactions that broadcasts these emitted events to all trails, and all trails must react before we go back in the stack. And of course, emits can nest, so they behave like function calls. So I'll show here an example. We have a internal event inc, like to increment something that receives a pointer to an integer. And here's an example of an application. I will await this event in a loop, and I will increment the pointer and await again. So this is like a function. And here's the main program that uses this event. I have a local variable v. I emit the event passing the reference. And how will behave? First, my program will reach the await, and then my program will reach the emit. And the emit will create a new intra-reaction and will block here. This assertion will not execute. So I will broadcast the event, and I will await this await, and I will do the increment here. Then I will loop await again for the inc, and only after everything happens is that I go through the assertion test. So it's important that this assertion test only executes after the intra-reaction terminates. So these mechanisms, it brings some richer control mechanisms. I talk about this in a paper. So a kind of static coroutines, because I can await inside these other bodies here, and also other mechanisms. Next, the internal determinism. So in STHL, if there is no control dependency between two statements, like in these calls here, the order, we cannot specify how they will execute. And also, if we write to some variable, we cannot access this variable in the other threads. And in cell, we do the same as was discussed also yesterday. We use lexical order. So if this code were written in cell, this would be called first, and then this other call would occur. And this is a very pragmatic approach. It's easy to do printf and understand the order of the printfs we will execute. Also, when we do graphical applications, we rely on this. We really rely on this. For example, we can have a behavior for the background of the game in parallel with a behavior for the scenario in parallel with the characters of the game. And we rely on this order because the redrawing will first redraw the backgrounds, then the scenario, then the characters. So they will follow the Z order based on the lexical order of the code. So it's very practical, but it's fragile. People also discussed this yesterday, and I agree. So we do a little bit more about this. So we have some very simple static checks. Let's see here an example. We have two inputs, A and B, and a shared variable X. And we have something in parallel. One waits A and access X, and the other waits B and also accesses X. As we saw from the semantics, A and B, they are never concurrent. This is the definition of timing in cell. They cannot occur at the same time. So these accesses are safe. By safe, I mean that I can flip the order of these statements and the semantics would be still the same. But if we take this other example, we only have A and it's similar, but both sides await the same event. So they are now always concurrent and we consider this unsafe. Now if we flip these programs, these trails, the semantics of the program changes, so we consider it to be unsafe. So we do these static checks based on the previous input. It's very simple, so it might give a lot of false positives. And we have 3 levels. In level 0, we consider both cases unsafe. Even this one, we consider unsafe. Level 1, which is the default, only this one is considered unsafe. So this one will compile. And in level 2, both cases are accepted because this example is still deterministic. And this is because of the uniqueness of inputs. And also the static checks, they do not affect the semantics. If we disable, the programs would still be deterministic. So there's a question, if a program accepts at most one input at a time, is cell synchronous? Well, I believe so because of the synchronous hypothesis. I believe I would define the language as synchronous if it follows the synchronous hypothesis, but I'm not sure if this is the correct answer. About the integration with C, we can use native blocks and we can write C code inside it. So this is normal C code. We only omit here the bodies of the functions. And here we have a program that uses these definitions. So when we are here in the cell side, we have to use this underscore to make trackable that we are using the C hat. This is outside of control of cell. And we assume that all identifiers are conflicting. So similar to how we do with the shared variables that I just talked about. So this program is unsafe because F and G are concurrent. But we can use some annotations to eliminate conflicts. So here we can put the annotations before, and we are saying that num is a constant. So it becomes green here in this code. We are also saying that ID is a pure function, so it's safe to be called in parallel with other code. And we still have this problem with F and G because they are both have side effects, so they are conflicting, but maybe they have compatible side effects. So we can annotate and say that it's safe to call F and G concurrently. And if we do this, they now become yellow, and it's safe to call them in parallel. So this is about the integration with C. There is still one more thing that is actually the most important about the integration, because when we abort trails with dealing with resources is very unsafe. So here's an example. I have a pointer to an external file. I open this file. I write to this file. I await something to happen. Then I write again to this file. And finally, I close this file. So it's a sequential program, very easy to follow. But of course, it's unsafe because we can call this in parallel with something else. And it might happen that this line aborts this when I'm waiting here and I do not close the file. So it's unsafe. So in this case, what we do is that cell enforces that pointer assignments must be finalized. So this code will not compile because of this line here. It will say that this line requires finalize. And what we do here is that we have to write something like that. We have to put the close together with the open using this finalize construct. And so we know that this code is safe because when this variable goes out of scope here, the finalize will be called and we will close the file. So this is an example of an external resource from C going to cell. So it's in the direction of C to cell. And we are preventing here memory leaks in the program. But there is also the other direction when we have a local resource going to C. So here's an example, similar or parallel. Here I have a local resource. This is a local buffer that cell is allocating in its memory. And I'm preparing this message and I'm sending a request. I want to send this message across the internet. So this call is asynchronous. And I have to wait for an acknowledgement of the driver to say that it is really sent. Again, this code might, abort, and this variable goes out of scope, and I'm still sending it. So maybe this variable, this memory is allocated to something else, and I start transmitting garbage in the background. So this finalize will cancel the message sending. And the last one that I want to talk today are the first class timers. So it's very useful for timers, watchdog, sampling sensor. In general, reactive applications take advantage of first class timers. First thing, Cell provides a dedicated syntax. So here we we can use time units to await. And the thing that matters more here is that we do delta compensation. So it's possible to have a mismatch between the system timer, the actual driver that is running the operating system, and my program timer. So suppose here, my program was preempted by the operating systems, and when it comes back, the system says that 15 milliseconds have elapsed, but I was awaiting only 10 milliseconds. So this means actually await at least 10 milliseconds. So what the system, the runtime does is that it tracks how much time it is late. So now it's 5 milliseconds late, and it will propagate to the next await. And if it's also a timer, it will go on and subtract from the delta and will continue executing until delta reaches zero or it reaches some other kind of await. This is, in this example is the didactic example, but this is actually very important because as we know in the synchronous semantics, time only elapses in the awaits. So here we are actually awaiting 11 milliseconds and here 12 milliseconds. The language must guarantee that this code runs first and this code runs second. So if we apply the same idea to the previous example, if we don't do this delta compensation, it could happen that this other code would execute first, and this would violate the specification of the program. So this delta compensation is very important. This is what I want to say today. Cell is about a 10-year effort, and we have some applications published that I believe are interesting. So for example, we took an open source game written in C++ and we wrote it in Cell. So the game was 40,000 lines of code and we had to rewrite 10,000 lines that were specifically reactive. So it was very interesting to exercise if the language is stable and if the dynamic features were sound. So the reactive part here are the animations, the button clicks, the screen transitions, all the main logic of the game is reactive. So we also had this paper that we implemented interrupt serviceable routines in the language. And when the language is idle, we could put the microcontroller to stand by automatically. So the programmer doesn't need to care about these mechanisms in the microcontroller. The language does everything automatically. We know that in synchronous languages, at least in theory, the program is always sleeping. So we could really reduce, for example, if you took Arduino as an example, we could reduce the consumption like 95% using this mechanism. For multimedia applications, also similar, a lot of dynamic behavior we could exercise with this. And also we did a virtual machine of Cell to do remote reprogramming in sensor networks. So also another application. So I believe this is it. Thank you. I'm open for questions now. Thank you.